Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at some things that maybe you didn't know are STEM. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. I'm really excited to introduce our two panelists tonight, Jessica Cahoot and Joanne Miltenberg. Jessica has taught all levels of biology, from co-taught to advanced placement at Reservoir High School in Howard County, Maryland. She was first introduced to the TI-Nspire in 2009 and has been using it in her classroom ever since. She became a T-Cubed regional instructor in 2015 and sees the technology as a great way to help students make real-life connections with science. Jessica, thanks so much for being with us.
Thanks for having me.
And Joanne has been in teaching for over 35 years, the last 25 at Farmingdale High School. Joanne was trained in 2000 by NYSUT and Texas Instruments to give technology-related professional development to teachers. As a T-Cube national instructor, she has led professional development workshops, conference presentations, and in-service training locally, statewide, and nationally. As a direct result of successfully integrating technology into her classroom, Joanne received the following honors. She has the Long Island University Teacher of the Year, Town of Oyster Bay Women of Distinction in Education, Nassau County Math Teachers Association Teacher of the Year, and the U.S. Department of Education American Star of Teaching, an award which recognizes innovation in the classroom. Joanne, thanks for being with us.
Thank you. Glad to be here.
We're expecting a large crowd, so your audio is automatically muted. Feel free to send any questions to Joanne or Jessica using the Q&A window on the right side of your screen. As a reminder, this session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. Once that recording is available, if you'd like to follow along, that's, I feel like, the best way. That lets you go at your own pace. You can pause and rewind the recording as necessary. So tonight, just sort of sit back, relax. We're going to be using the chat window to send general messages, but please try not to necessarily follow along with your handheld or your software tonight. Just wait for the recording and follow along with the recording at that point. We hope you don't have any audio issues tonight, but in the event that you do, you can try selecting Communicate in the WebEx menu and choose Join. And if that's not working, if you continue to have audio issues, I just put my name next to, there's a small icon on my screen. It looks like a little telephone. And if you can find that participant window, which for me is just labeled participants, in the bottom left-hand corner of that, there'll be a little phone icon. So if you continue to have audio issues tonight, find that phone icon, and it will let you call in using, say, a cell phone. At this point, Joanne is going to discuss our agenda.
Our agenda tonight is STEM, what it is and what it isn't, STEM activities, stay tuned, One Giant Leaf, Haunted or Hoax, online resources, and our webinar giveaway, complimentary registration for the T-Cubed International Conference.
Thanks, Joanne. And Jessica is going to talk through some expected outcomes for tonight.
We're going to show how such topics as photography, music, and gardening have elements of STEM that can help students develop 21st century learning skills, demonstrate how to incorporate non-traditional STEM activities into your math or science classroom, and highlight resources available to help you provide real-world relevance to math and science concepts.
Thanks, Jessica. Joanne, it's all yours.
Thank you. Okay, what we'd like to do tonight is start with a few questions that you can answer in the chat window. So the first question is, what is one thing related to STEM?
So feel free to put your answers in the chat window. We'll read them out as they come in, and hopefully you'll have some good discussion. So we've got engineering, problem solving, science, technology, engineering, math, engineering projects, connecting math and science,
lots of
problem
science.
solving. Science is amazing.
Architecture.
Yes.
Technology, problem solving, art.
So there's a lot of different answers, which are great.
Okay, we're back to science, modeling. All right, I'll share a few that we had shared. Instill a love of learning, fun, a break from the normal routine, STEM jobs, not just engineering, women in STEM, encourage girls to get involved in high-level math and science, and prepare students for jobs not yet developed. Mathematics connections with some fun, I see.
Always.
Fun. All right. Jeff?
Our next question is, what is a misconception about STEM? So go ahead and fill your chat window again with what you think are some misconceptions.
Hard cuts.
Yeah, math and science are hard. You have to be good, you have to be smart. It's for nerds. There's some truth to that. Just kidding. Only engineering. Special education kids can't do it, so it's only for only for certain groups of kids. It's sad. A formal class. Okay. All right, well, let's see what we have put. So that every lesson has to have all four components, and that's not necessarily true. It doesn't have to be all engineering or all technology or all science or all math, that it's integrated. I thought I had no E. Turns out most of my lab follows the engineering problem-solving processes or the science and engineering practices of NGSS. A lot of us do a lot of these you know, asking questions, planning and carrying out investigations, these science practices that are so embedded in our everyday science lessons anyway, or have no time. STEM can be integrated in anything and need a lot of equipment and money. You can do STEM with a very low budget, whether you're making models on a desk with dry erase markers or, you know, just doing something simple.
All right, and Jess, the I have no time, in the math curriculum, we don't have labs like science people do, so we have to figure out how we're going to fit it in without, you know, in place of a traditional lesson.
Right, learning while doing, it's the best way.
Right. Our next question, where is STEM in music?
All right, so where are the musicians out there? You can add some ideas. Waves.
I can give some hints. Here's some hints. Here are some hints. Patterns. Fractions, sound waves. Language. Amplitude. Okay, and we have some of them were mentioned: fractions, Fibonacci sequence on the keyboard, sound waveforms, roots and powers, ratios, and frequency.
And we have one last question we'd like you guys to participate with, which is one skill you think is related to STEM.
Critical thinking. Imagination, problem solving, critical thinking, math concepts, teamwork, planning solutions, problem solving, collaboration, communication, supporting evidence, enjoyment.
I think they got a lot of them.
Yeah.
No.
Student-centered. It's like science.
So many of you said a lot of these skills: problem solving, analysis, collaboration, creativity, organization, leadership, being able to read and follow directions. But you guys, you did it. You hit the nail on the head with this one.
Awesome. Right, so that's the end of the our questions. So I am going to start. And there are a few things that I'd like to show you before I start. I know how difficult it can be to follow along, as Mike said, when you're trying to do the work. So I have some files that will let you go through the lab at your leisure when you can pause the video. So my teacher notes are in Word, PDF, Promethean flip chart, and Smart Notebook format. And the notes guide the teacher through the lab using sample data. And there are instructions for the teacher to use with the students. And troubleshooting and extension ideas. The lab I'll be using is called, is the Sound Waveform Lab from Real World Math with Veneer. And it's in PDF format. And it was revised to be used in place of my traditional lesson on sine curves and vertical and horizontal phase shifts, frequency, and amplitude. So the lab has objectives, a step-by-step procedure for data collection, instructions on how to create a problem with a copy of their data prior to starting any calculations. One problem will be used for the student's cosine model, and one problem will be used for the handheld's built-in regression tool. Guided instructions to find all of the information necessary. So we have period, frequency, amplitude, our horizontal phase shift, and directions for the manual cosine model curve fit, as well as a series of questions asking the students to evaluate the parameters and make adjustments if necessary, and directions for a sinusoidal regression using the handheld to compare to their own model.
And Joanne, we had a question about, is this available for the TI-84 rather than the Nspires as well?
I have an adjustment for the TI-84. You can't do everything exactly, but you can do it on the TI-84 if you have a CBL2. That's the computer-based lab system. So I'll speak to that when we go through it. Okay, so I'm using the TI-Nspire to do it tonight, and I have two TNS files. Our files are just a single page file. Stay tuned is used with the TI Navigator system, and this allows us to collect the data from one student's handheld and send it back to each group member to continue the lab work together. Stay tuned possibilities, which is the file I'll be using, has previously collected data for practice and demonstrations. And the teacher notes and the TNS files both have sample solutions. Now, I mentioned in the beginning, and I know you spoke about the 84, this comes from the Veneer book, Real World Math, and they do have a prototype. What I revised, they have in for the TI-Nspire and for the TI-84. So that would be real world math with Veneer. Okay, I'm going to start with two short video clips to show the lab setup and data collection on page 1 of the lab. So the student will need TI-Nspire or TI-Nspire CX handheld, a TI-Nspire lab cradle capable of collecting 100,000 samples per second with 3 analog ports and 2 digital ports. I use tuning forks with a variety of marked frequencies, but they don't have to be different. A rubber mallet or something not too hard to strike the tuning fork with or on. A hard surface will damage the tuning forks. A veneer microphone probe covering the range of the human ear. The microphone probe is not compatible with EasyLink. The microphone is connected to the channel 1 interface of the lab cradle. The TI-Nspire handheld is placed in the lab cradle and locked in at the bottom, and the veneer data quest page should come up automatically. If it doesn't, students can insert a data quest page. We strike the tuning fork and hold it as pictured in the lab and start the data collection. Holding the tuning fork like this, I haven't had any problems with the entire class collecting at the same time. And again, those of you who do use the TI-84 Plus, you can use the microphone probe with the CBL2, that's the calculator-based system, and modify the lab. I know it's difficult to see, but because the data collection in this video used the default settings, all of the data collected is above the x-axis. This is procedure step 5, and we give the students the directions for making the x-axis the midline. So with the room quiet, they go to Menu, Experiment, Set up Sensors, choose Microphone, and tab to 0. They enter or click the mouse. The word 0 is put in the lab because the students were changing the displayed precision from 3 to 0 and never changed the midline. Now the sound pressure, which is by my arrow, the reading is hovering around 0. This time we collect our data. The midline will be the x-axis. So again, we strike the tuning fork as pictured in the lab. And we encourage our students to save their data and check with the teacher to see if there's a need for another collection. So they're saving the data. And because I use the Navigator system, I take advantage of the screen capture option to try to catch mistakes early so that we don't have to fix it later on.
And Joanne, we have a question from Jenny of where did you get your tuning forks?
Amazon. It was much, Amazon was, I mean, and I don't know who you buy from, but Amazon was much cheaper than Science Supply. Like that entire set was about $15. So this is my data. Is there anything else, Jess, before I start?
No, go ahead.
Okay, this is my sample data. So we start by counting the number of cycles from the first peak to the last peak. We also need the coordinates to calculate the period and frequency. So to get accurate data, we have to click and then arrow because you can see it jumping. Although you only see a few points on the graph, there are 301 points in our data collection. We need the coordinates of a minimum to be used to find the amplitude, and any time value for the horizontal phase shift. Following the calculations, the students record all of their information in the data chart. So I have 7 cycles. I have a first peak and a last peak, and a minimum value. We subtract our first time from our last time to get the change in time of 0.027. Divide the change in time by the number of complete cycles for a period of 0.003857. I divide 2 pi by the period to find a frequency of 1,628.97. And you can see that the denominator here we get by arrowing up to the 0.003857 and hitting enter so that we don't round during our lab. We take half the difference between the Y min and the Y max to find an amplitude of 0.139. In my cosine model, I'll use a time value for the first peak of our 0.0013 from the first set of coordinates. Students are given the instructions to enter their data into the cosine model for a manual fit. And you have to be careful. Sometimes the handheld doesn't recognize implied multiplication, so we do ask them to use multiplication signs. To do our curve fit, we go to Menu, Analyze, and I said curve fit, I want Model. So we go down to Model, and you can see it starts out with the linear. We want to put in A times cos B times x minus c, and close both sets of parentheses. We do ask the students at this point to hold their shift key down and arrow to the left to highlight their model, and copy it, Control V, Control C, for later use. They tab or click to OK, and they enter the amplitude, the frequency, and the phase shift. My values are here because they were previously entered. Doing it for the first time, A, B, and C will all show up as 1.00. So I have an amplitude of 1.39, my frequency of 1,628.97, and my horizontal phase shift of 0.013. We tab to OK, and we have our cosine regression. Jess, any questions?
Not yet. Oh,
okay.
We have, sorry. What level would you suggest using this activity with?
This activity, I would say, as soon as you introduce trigonometry, this is very revised, and as I said earlier, we had to save time, and so we actually used this activity to teach horizontal and vertical phase shifts.
And we have another question of, would this lab work if a student played an instrument into the microphone instead of using a tuning fork?
I definitely wanted that question later on, but I've included at the end of this, and we'll get to it, some samples of a dollar store recorder and students' instruments. So that takes care of my asking the questions later on how they would extend it. But yes, absolutely. You just have to look at where you collect the sample from, and you'll see that with my piccolo or with the student's piccolo, how the curve can vary. So we're okay?
Yep.
Okay. We do ask in the analysis section the students to examine their parameters. And so there are two ways of adjusting their parameters, and it's based on which operating system your handheld has. With the most recent operating system, if you go to your actual cosine model, there are up and down arrows to adjust your amplitude, your frequency, and your phase shift directly on the model, which is much easier for them to work with because it's like a friendly window. And you can also enter an entirely new value by just double-clicking and changing it. So it's very user-friendly. With the early operating system, you wouldn't see these arrows on the right-hand side. And so you actually have to go back into the regression, which we do the same way that I did the regression initially. We go to Menu, Analyze, Model, and this time we choose Add. And this is when Control-V comes in very handy. So we Control-V that for the model that we copied before and say OK. And as long as you bring up the same model, your former values will be there. And so we can adjust the previous parameters and get our new model. But they will have to go back in each time to change their parameters. Checking in, Jess. Any questions?
There's just a lot of people that love your activity.
Oh, good. Thank you. I don't get to see that, so thank you. All right. This is the data page that was copied and pasted following the initial data collection. So it's used to do the handheld's built-in sinusoidal regression. So the built-in regression is Menu, Analyze, Curve Fit, and we choose sinusoidal. And this is really nice. Before I take out this window, it's nice because the students get to see that their work actually looks better than the calculator's built-in regression tool. But because the students only see a handful of points, we do ask them to use the Send to Data and Statistics option so they can see that the regression does lay right between all of the 301 points. So we would ask them to go to Menu, Send to Data and Statistics, where they can see all of the data that we've collected. And then on the Data and Statistics page, Menu, Analyze, and go to Regression, and choose sinusoidal.
And Joanne, there was a question about, is there some sample data somewhere if we don't have the microphone probe or the lab?
I'm making this file is available to them in the files for this webinar. So the Stay Tuned Possibilities that I'm using now is one of the files that that they'll have access to. And yeah, let me just go up this way, Control up arrow, and you can see that I have separate problems for each section with data that works, and then come down to the bottom, and these were our instruments. And the, oops, back to the bottom, sorry. I have the recorder and the instruments. So plenty of sample data. Okay. Often the handheld's built-in regression will result in a singular matrix error, which is another reason for multiple data collection and another advantage to using the manual cosine or a sine model. And so if you wanted to also incorporate into the lesson the difference between cosine and sine just being a horizontal phase shift, you can have students do the sine model on their own also. So we're going to go Menu, Analyze again, Curve Fit, Sinusoidal, and you can see our singular matrix error. The singular matrix error means that the data points collected were either all in one single cycle of the sine curve, or one of the inverse matrices used in the calculation has an undefined denominator. So if this were to happen in a lab and we weren't doing a manual fit, the lab would be over. So students wouldn't be able to answer. Right. If you do use the default settings, the data is all positive. And so we have the addition of a vertical phase shift. So the midline and the amplitude formulas change, as well as the cosine model. And this is all in Stay Tuned Possibilities for you. So our period and frequency and horizontal phase shift are calculated the same way. And the midline, the amplitude, and the vertical phase shift are calculated with new formulas. So the cosine model, you can see now has, can't see yet. You can see has amplitude, frequency, horizontal, and vertical phase shifts. Any questions?
I think we're good right now.
Okay. So the pages 7.2 to 7.8, I've included data results from different notes from a dollar store. Let me go through this. This is a dollar store recorder, which was used instead of tuning forks. And it really did a nice job. And I was pleasantly surprised since I was asked. I told my students that I'd be interested in using instruments next year, and I couldn't believe how many of my students with their friends came to my room on their periods off to play one note for me. I told them all I wanted middle C, but it showed me how I could include a whole section of my class that I don't usually teach to in the math classroom, and they were really excited about sharing it with everybody. And so we have 3 violins and 3 French horns, which I thought even after I asked her to play it 3 times, the curves came out very similar, and 2 piccolos. This was taken from the front of the piccolo, and this, which was a much better curve, was taken from the end of the piccolo. The higher frequency tuning forks and the higher pitched instruments are why we ask our students to change their time window down here to 0.01 before they graph, because it's much more manageable. And finally, after every lab, we ask our students to check our work and make suggestions for future labs or suggestions to make our labs better. One of our students suggested that we extend this lab. And you can see the form that we use. He said we should calculate the period of one wave, then use frequency equals 1 divided by the period to find the frequency, and then, calculate the percent of error between the marked frequency of the tuning fork and the frequency of their data collection. And he was nice enough to include his work for us. So it was really nice, and clearly I'm impressed that by the fact that our students, when asked for extensions for us, clearly understand the connection between the math and the science. So Jess, I'll take any questions that we have, or I'll pass the ball along to you.
All right, well, we got one question of how much time do you allow for this lab and any extensions with it?
We usually aim, since we do horizontal phase shift, and we do our traditional sine curve on the first day in our class, and horizontal vertical shifts after that. We use 2 days. We start out by giving them the lab, having them read through it, get into their groups, and take their data collection. We make sure everybody has, or everybody who's present has their data the first day, and then the next day they work on it together. I did mention that I have the single page stay tuned document. We just send this one page out via the Navigator system. And so when everybody collects their data, the person who's doing the collection sends the data to me, and then I send it back to anybody who's working in the group so that they can work on it together the second day.
All right, any more questions for Joanne? Could you use the innovator and code the notes to be played instead of using the tuning forks?
Yes, you can use the innovator.
All right. So you want to pass the ball to me?
Yes, I can.
All right, well, welcome everybody again. I'm going to be showcasing a couple of the TI activities. This first one is One Giant Leaf for Mankind using the TI-Nspire CX and the TI Innovator Hub. As a biology teacher, I was super excited for this activity because it deals with a biology concept of photosynthesis. And being a biology teacher, sometimes I feel like we get left out of the STEM conversation because people tend to think that biology is not very engineering or math heavy, but I think that's completely untrue. So for this part, I'm just going to kind of highlight a few of the pieces of this activity and kind of skip through a bunch of pages. But to give you kind of the storyline of this activity, students are going to be playing the role of a horticultural engineer. So a lot of these activities highlight a STEM career that some people may not even have heard of, like a horticultural engineer, which incorporates agriculture, engineering, computer science, and plant science. And the students are going to design and build a model greenhouse for the International Space Station, which you should see here, and so that they would be doing some testing for some long-term plant production or food production for extended space missions. So this activity incorporates a lot of science concepts, integrating biology, earth space science, chemistry, physics, including math and technology using the innovator and engineering practices of building models. So it really incorporates all those STEM acronym of science, technology, engineering, and math. So it's a really good example of what you can do in your classroom that really use some STEM. So the basis of this activity, again, is to generate a greenhouse. So they're going to create a model. And this greenhouse is not just like any greenhouse that you would build down here on Earth, but it's on the space station. So they have to take into account those special circumstances where light behaves differently because there's no atmosphere in space. So instead of the light scattering, it comes in at a single point. So they have to take that into consideration and think about the limitations when they're developing their models. So they also have to understand the basic principles of photosynthesis. So there's some activities built in here to help students understand the plant cell. So here's a little magnifying glass that students can go through and identify the different organelles of the plant cell. They get into other things. There's questions about this. They can go through and understand some of the raw materials needed for photosynthesis. This particular activity was written for middle grades, but there's no reason that it could be beefed up for high school because photosynthesis is also part of the curriculum, at least in Maryland it is, for high school biology. And then also incorporating the photosynthesis reaction, knowing what the reactants and the products are for photosynthesis and how this energy is converted from the sun, the solar energy, into chemical energy to produce food. And the food that we're producing in this activity are yams. So the students are simulating the production of yams from plants that they will grow in their model greenhouse. Also, it talks about the cycling of matter and the flow of energy. And our little astronaut here actually goes with another activity that goes hand in hand with this one called One Giant Bite for Mankind. So it's using cellular respiration and figuring out how much our astronaut would need to eat. So in this activity, we're making the food, and then in the cellular respiration activity, the astronaut needs to eat it. So it works really well together. So now that we have some research, students should have a good understanding of photosynthesis. They should have a good understanding how their limitations of light is different on the International Space Station, and now it's time for them to think about how they're going to take that information and build a greenhouse. So the parameters that they're going to have is that they have to produce at least 800 calories from a single plant in 3 months. So this will be run in the simulation. So when they're generating this model, they have to think about the size, the shape, the materials used to harness this light to maximize the solar energy for their plant. So I will show you what some examples of materials would be. And the more materials, the better. Just throw out anything that you can think of. And this is, again, that part of that STEM skill of being creative. By giving them a wide variety, you never know what they would come up with. They're pretty ingenious little guys. And so now once they kind of have a chance to come up with some model, they're going to test it. But first, as a teacher, you need to establish a control. And to establish the control, you are going to use the light sensor, and I'll show you what that looks like too. So this would be the control. So here's the TI Innovator CX attached to the Innovator Hub, and that is attached to the light sensor. So initially, you want to set up the control in your classroom, and you want it to be below the unit of measurement of 100 lux. And so that's, they are then designing something that will increase that to make your yams grow. And so we have our little yam calculator down here. And so when they collect their data, they'll see the change of the carbon dioxide being used up, the oxygen being made, and the energy being stored. You can see our little tubers beginning to form and how much calorie is being produced over time. This is also a surface, or the surface area of the plant. Right now, I didn't set it up as well as I should have. It should be 10 by 10, but we'll go with 15 by 15, or 15 by 10. That will be our control for now. But we'll see if that makes our 800. I don't know if it's going to. It's at 40 days, and it's going to be our max at 60 days, and we will see. So I don't know. It's going to be close, and doesn't look like it. Or maybe. We'll see. Just under. So I need to try again. And so what students can do, they can take their design, try it out, test it out, and if it works, great. And if not, if they fail at it, that's a great part of engineering design, is that they have a chance to retweak it. And it becomes this competition of who can make the best design, even within a group of what can we do to make it better? What can we do to get it to that max number as fast as we can? How can we, you know, get the highest calorie in the lowest number of days? And so it just allows for that collaboration, which is a lot of fun because, you know, they always want to beat each other. Competition is always a big thing when it comes to middle and high school students. And so this time around, I think we'll do it. And so we reached our goal. We've created our little tubers all in the nick of time, actually less than 30 days. And so we can also analyze this data. So here is our energy production graph where it shows our energy rate, energy over time, and we can add a movable line. So we can then determine what the rate of the reaction is. And then from here, students can kind of get a baseline of where things are, and then they can manipulate and investigate other variables. So they have, back in the simulation, they can change the surface area of their leaf, and as they change that surface area, you can see the leaves increase. Got more leaves there, lots of leaves. And they should see that there's a proportional relationship. As you increase the surface area, you're going to increase the amount of energy produced, because now we've gone crazy with the amount of oxygen made. We did it under 20 days, so really fast. And so they can also tie in this graph, the oxygen made versus the carbon dioxide, as far as the oxygen increasing, the carbon dioxide being used back to that raw material, seeing that relationship between what the plant needs, what the plant is creating, and how it's all working in relation to the energy stored. I personally really like this activity, not just because it does talk about biology, and biology is just awesome, but I think it really incorporates a lot of skills that students need in STEM. So it has problem solving and analysis and collaboration and creativity that students can really work with. And another thing is that students can kind of take this activity and extend it. So as Joanne was talking about with her extension, with her simulation, some ideas for this extension would be, have students think about what would the limitations on the International Space Station be? So the background is that it orbits the Earth every 90 minutes. So how often would it be exposed to sunlight, or how would students get it to move in order to reach the maximum amount of sunlight? Or even something that I'm interested in is, now that students have had a chance to work through these practices, practice creating this model, and learn these skills to apply it to something in their own backyard or schoolyard, and that most students probably won't be going to the International Space Station. But if they could take these skills and apply it to, like, creating a school native plant garden, where they design a native plant garden where they take into account the surface area of space, the amount of sunlight available at a given part of the school, at a given part of the day, a given part of the year, the types of plants available, and how much sunlight that they would need. A lot of these skills built in this activity can be a launch pad for other types of activities that students could run with. So does anyone have any questions for me for now?
There are no questions, but you should know this is nice, and it's a nice activity, and it's very interesting, and they love this activity.
Well, that is awesome. I'm glad to hear it. It is a really awesome activity. If there's no questions or comments about this activity, do you want to move on to the next one?
Sure.
All right, so the next activity, which is one of the new STEM behind Hollywood activities, it's called Haunted or Hoax, so pretty scary, right? But it's a story of a photojournalist, and which is another unexpected STEM career. You don't normally think of photojournalists as STEM, but it does relate. As we've talked about, a lot of things need those STEM skills. And so the storyline behind this activity is that this photojournalist is on assignment behind the scenes of this fictitious popular TV show called Ghost Nabbers. And so this photojournalist goes in and takes pictures and asks probing questions, and spoiler alert, she uncovers the fake story of this ghost story that they're promoting, using her knowledge of science and math and technology and engineering, so, well, sort of. So there are some elements that can be used and talked about in STEM for this activity. So kind of showing you where some of the science and math are integrated, we're going to be talking about the electromagnetic spectrum. And so there's this great simulation that has a slider that shows the visible light spectrum, and as you move it, you can see the different colors of the visible light spectrum, and then it goes away. And then here are the colors.
Right, so the wavelength increases as you go from violet to red. And the wavelength is measured from peak to peak. And then when it gets past red, it becomes infrared, and that's why you no longer see it, because it becomes a heat source.
Beautiful. And the other part that I really liked was this simulation that shows a camera, and it goes into the diameter of the camera aperture and the amount of light it takes in. And so you see this very scary cemetery scene, and as you increase the diameter of the aperture, you see more light coming in to the point of, oh, there's a scary ghost person, but is it really there? Or is it just a trick of the light? So I really like this activity because it sheds some light, pun intended, on a unique STEM career of photojournalism, because again, most people don't think of photojournalism as a STEM career. But you know, this person needs to understand what they're reporting on. In this case, there's some having background knowledge in the electromagnetic spectrum, wavelength, frequency, how their equipment works with the camera aperture and its limitations. They were able to, you know, analyze the information that they were given and that they collected, as well as communicating their ideas, which is something that we all want our students to be able to do. So they're able to communicate their ideas clearly and intelligently. As a science teacher, we all want our students to be scientifically literate. I'm sure math teachers want their students to be mathematically literate, right? And it all connects together. You can't have one without the other. And that's the great thing about STEM.
Also, Jess, before you pass it back to Mike, the participants should know that all of the activities like this that are on the Texas Instrument website come with a student version and a teacher version, which gives you suggested answers to the questions that they're being asked, in addition to the TNS file.
Right, yeah, you always have the answer key. Well, are there any other questions before we hand it off to Mike?
No, I don't think so. I think there's just a question about the real-world math book, which I will respond to in chat.
All right.
Thanks so much, Jessica and Joanne. As we begin concluding things tonight, if you have any last-minute questions for Jessica or Joanne, please feel free to try and get those asked. I know they'll do their best to get them answered. I'd like to share some information on our website, education.ti.com. Some of the things that were used tonight were, again, available on our website, as Jessica had mentioned. And if you move under the Activities tab, you'll see this grouping of STEM activities. So we have the STEM behind Hollywood, STEM behind sports, STEM behind health, and STEM behind NASA. So, for instance, let's say you check out the STEM behind NASA. You can discover some activities. And so, for instance, we have an activity called Heart to Heart. And I think Jessica had mentioned that each of these activities that are available come with not only the student worksheet, but also the teacher notes. And I don't know if you feel the same way I do, but sometimes these activities I've used start to finish, and they work great. And sometimes I just need a visual or maybe some filler to support some content that I'm teaching. And so sometimes I just use maybe a page or two of a TNS file, TI-Nspire file, and I don't bother with the worksheets. So it just depends on sort of what my needs are and what my students' needs are. But I want to make sure that everyone's aware that you could find more information about STEM activities on our website.
Mike,
Yeah.
There was a question. I know that the one which is easier, faster for me to answer than to type, that Haunted and Hoaxed is on the Texas Instrument website under the STEM. But they were also asking where they get the access to the files that we used.
That's coming. Just give me a few minutes here.
Okay.
It's on its way, including the Haunted or Hoax. So all of the files that were presented tonight by Jessica and Joanne, I have those compiled, and I'll be hanging those out here in a few minutes. So again, most of them are publicly available, but either way, you're going to get them tonight anyway. So just hang tight. So whenever you leave the webinar tonight, a brief survey will automatically appear in your browser. And your feedback really guides us as we plan future online events. So if there are things that went well tonight, please let us know. If there's things that we probably need to work on or things that we should consider for future webinars, whether it be content or technology, again, please feel free to let us know. We hope you share your thoughts in the post-webinar survey. So I just looked at the calendar, and March 10th is coming up pretty fast, and that's going to be the start of the T-Cubed International Conference. We're really excited to have it in Chicago this year. I don't know if anyone is looking at those pictures at the bottom, but you might notice that the middle picture and the person on the left, I think holding a CBR2, is our very own Joanne Miltenberg. So very famous. You didn't know that you were in the presence of greatness tonight, but all joking aside, Joanne and Jessica, as well as myself, we're all going to be at the T-Cubed International Conference, and we'd love to see you there. Earlier, Joanne had mentioned during the agenda that tonight we're giving away to one lucky winner a T-Cubed International Conference registration, and tonight's lucky winner is William Taylor. So William, congratulations. Again, we hope to see you as well as everyone else at the T-Cubed International Conference in just a couple short weeks. You guys were really great in the chat window, asking lots of questions and had some great comments. We'd love to hear you continue those conversations on any of the major social media outlets. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents that were used tonight, as promised. And if you happen to be having any issues with those links tonight, have no fear, you'll automatically get a follow-up email in a couple of days, and in that email will be a link to the certificate, a link to the documents, as well as a link to the recording. And if you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. After tonight, if you need any post-webinar follow-up, you have some additional questions or just need more information, feel free to give us a call at 1-800-TI-CARES or drop us an email at ti-cares@ti.com. Thanks so much, Joanne and Jessica, for everything you shared tonight. I really appreciate it.
Thank you. It was fun.
Yeah, my pleasure.
And again, thanks so much, everyone, for joining us. We hope to see you back online next week. Have a great night.